Thank you for visiting my poster. In this poster, I'm going to discuss how I took inspiration from the design and biomanufacturing of marine shells to create a multifunctional composite. But before that, the key question is, why do we need such materials? Well, Singapore and many other countries now want to make a decisive switch to environment friendly materials and less resource intensive manufacturing approaches. The Singapore Climate Action Plan makes that very clear, is to use bio based materials. One such material is chitosan. However, if we want to use chitosan for industrial applications, an important factor is its mechanical property, because mechanical properties are an important determinant of a material's load bearing capability, which is crucial in industrial and biomedical applications. Now, if you see in figure 1, where strength and modulus of most conventional materials are plotted, chitosan's mechanical property is actually quite inferior to most conventional materials. Now, surprisingly, the marine shells from which chitosan is derived, which is called nacre, is way up in figure 1. Now, the reason for that is that nacre is actually a composite which is made of chitosan and calcium carbonate platelets, where the platelets are arranged like bricks in the chitosan matrix. So I took inspiration from this design and first investigated the synthesis of mineral platelets by an approach called biomineralization, which is similar to how these platelets get formed in nature. Now, most importantly, biomineralization happens at room temperature and just requires a supersaturated solution of calcium chloride mixed with polyacrylic acid in the proportion given in the method section. What I observed is that mineralization in the absence of polyacrylic acid results in the formation of scattered rhombohedral crystals shown in figure 2a. On the other hand, biomineralization in the presence of polyacrylic acid results in the formation of calcium carbonate films as shown in figure 2b. When we extended the approach to chitosan films with a textured surface on it, we observed the same phenomena. The films followed the underlying textured surface, as you can see in figure 2c and d. Next, we developed a strategy to manufacture a composite using these textured mineral platelets. We stacked the films containing the platelets so that the textured sides face each other and infuse them with silk fibroin. And based on our FTIR results, silk fibroin helps bind the layers strongly together. And finally, after drying, we have a nacre-mimetic composite with alternating layers of minerals and chitosan as shown in figure 3a. And as you can see in figure 3b, these layers are actually interlocked. Now for comparison, we also prepared control samples with only planar mineral platelets, and they obviously have no interlocking across the layers. Now, we found that the interlocking actually helped increase the tensile strength of the composite, 85% higher than that of the control sample. In fact, the tensile strength of our nacre-mimetic composite was higher than the previous examples of nacre-mimetic composites in literature with the same composition. Which is at least 10 times higher than that of chitosan and is also closer to that of human bone as shown in figure 4. And most importantly, we studied the behavior of mammalian stem cell on the composite and found them to be alive after a week, indicating their biocompatibility. So to put it all together, as shown in figure 4, we now have a nacre-mimetic composite made using chitosan, which exhibits a higher tensile strength and modulus than that of the constituent chitosan. For its manufacturing, we developed a biomineralization approach that is green and less resource intensive. And since the nacre-mimetic composite is biocompatible and has mechanical properties similar to that of bone, we are further studying its biomedical applications right now. Thank you very much.